In this video, we're going to work through an exam question on magnetic flux linkage. Pause the video now and try all parts of the question. So we are given a graph of magnetic flux linkage against time. So it's really crucial before we can do any of this question that we really understand what magnetic flux linkage is. So we have been given a clue with the units, and units are so useful to unpick what's going on, especially with something like this, which often does cause confusion. So flux linkage is Weber turns. So what it is the product of the magnetic flux and the number of turns. It's BAN, or sometimes it's written as phi n, because phi is obviously BA, and n is the number of turns. And we're told there's 400 turns, which will be important later. We're told there's a cross-sectional area of this, which will be important later as well. So the first one is calculate the frequency of rotation of the coil. Now, to be fair, you actually don't need to know what flux linkage is to do this question. This is simply saying, how can we get from some kind of time graph with a wave on it to frequency? Well, we know that frequency is 1 over time period. What is the time period of this? We can see that it's 10 times 10 to the minus 3 seconds. So we can work out the frequency, which is 100 hertz, 100 times per second. Calculate the magnetic flux density of the magnetic field. So if you remember this equation here, it's really easy. So flux linkage equals BAN. So we can rearrange to find the magnetic flux density, which is obviously the flux linkage over AN. So the flux linkage, what is that? Well, we obviously need to pick really the maximum value of the flux linkage. So 2 times 10 to the minus 2, and then divide that by the area of the coil times by the number of turns. Plug all the numbers in your calculator and you get 3.1 times 10 to the minus 2 Tesla. Show that the maximum electromotive force induced in the coil is about 12 volts. So this is asking for the crucial relationship when we're talking about induced EMF. The EMF is the rate of change of flux. There is a minus sign there, which tells us that the direction of the induced EMF opposes the change that creates it. That's Lenz's law, but that's actually not needed here. Now, this is true, but because there are more than one coil, we need to slightly modify this and say that it's N delta phi over delta T, because every single coil is going to experience the same field through it, so we need to multiply that number of coils. And then we know that phi is BA, so it becomes BAN over T. So now it's a case of plugging in the numbers. We know what B is, we've worked it out. We know what area is, we have it here. And we know what N is, 400, divided by the time. So what time is this? Part III. Show that the maximum electromotive force induced in the coil is about 12 volts. So for this, we need to know that the EMF is the rate of change of flux. There is actually a minus sign there to show us the direction of that it opposes the change that created it, which is Lenz's law, but we don't actually need that. But we do actually need to take into account the fact there are more than one coil here. So it becomes phi n, because each coil will experience the same flux through it. So what is this telling us? This is telling us that EMF is the rate of change of flux linkage. And actually, what have we've been given here? We've been given a graph of flux linkage against time. So we need to know the rate of change, which is the gradient, and we need to know the maximum EMF. So that's going to be the maximum gradient. So we need to pick a point on the graph where the gradient is a maximum. So I've picked this point here. You could also pick this point here or this point here. And then you need to find the gradient of this graph. So I've obviously got a change here. I've made it nice and easy. I've got a change of 4 times 10 to the minus 2. And I'm going to divide that by the change in x. So from here to here, that is 10, 16 squares. So that's going to be 1, 2, 3, 4. That's going to be 3.2 times 10 to the minus 2, so 3 seconds. So that will give us an EMF of 12.5 volts, which is acceptable because that is about 12. Part B, hence calculate the maximum power dissipated in the resistor. So this is now a slight change. This is going back to kind of year 12 physics. We've got a power, we've got a resistance. So what is electrical power? Well, V squared over R comes to mind, seeing as we just worked out an EMF. Obviously, power is also I squared R or IV, but we don't really have anything about current here. So this is by far the easiest. So 12 squared over 150 ohms is going to give us 0.96 watts.